a 6-ton cylinder of aluminium, cooled to within 50 thousandths of a degree of absolute zero. A microwave generator, which delivers signals of hundreds of thousands of watts. An elegant and colossal radio telescope in Puerto Rico. The common effort toward which these and other modern instruments contribute is the probing of Einstein's general theory of relativity for possible flaws.
Today, the testing of general relativity involves large expenditures of resources and human efforts. A theory which describes such an exotic end product to stellar evolution as the black hole, and which is an indispensable ingredient in the description of the life history of the universe as a whole, deserves such an investment. But in 1915, when the first experimental predictions of the theory were made public, they may have seemed to concern only small and abstruse astronomical effects. The first, of course, is the gravitational redshift, which has been investigated rather inconclusively by astronomical means up until the 1960s, when it was measured on Earth for the first time by Pound and Rebkin. The second prediction of general relativity concerned a nagging anomaly in the observations of the orbit of the planet Mercury. The problem involved the celebrated Newtonian prediction that the orbit of an isolated planet around the Sun is an ellipse, and this ellipse should maintain a constant orientation orbit after orbit. But Mercury isn't an isolated planet. It has companions in the solar system whose gravitational influences disturb the orientation of the orbit of the planet Mercury. And this causes the point of closest approach, called the perihelion, to move about from orbit to orbit in a motion called perihelion precession. But the observations of 19th century astronomers had shown slightly more precession than Newtonian theory could take account of. A small residual precession of 43 seconds of arc per century, but unmistakably there. Explanations were sought within the Newtonian scheme, but none proved viable. And Einstein knew of this discrepancy all through the period 1907 to 1915, as he struggled to create the general theory of relativity. Imagine his emotion then in 1915, when, having created the general theory, he applied it to the Mercury problem to find that it explained perfectly the missing 43 seconds of precession, as Einstein himself expressed it.
Years of anxious searching in the dark, with their intense longing, their alternations of confidence and exhaustion, and the final emergence into the light. Only those who have themselves experienced it can understand that.
The third prediction of general relativity is that the curvature of space-time produced by the Sun would cause the path of a light ray from a star that passes close to the Sun on its way to us to be slightly bent. We would observe the effect as a slight displacement of the star's apparent position in the heavens when the Sun was close by. But again, the effect would be a small one, in the region of 1.75 seconds of angular displacement. And the only time one could observe the star in close proximity to the Sun would be at a moment of total solar eclipse.
The Cambridge professor of astronomy, Arthur Eddington, was one of the first people in this country to read and digest the Einstein 1916 paper containing the light-bending prediction. He and the then Astronomer Royal, Sir Frank Dyson, soon realized that the forthcoming eclipse of May 29th, 1919, would provide an exceptionally good opportunity to test it. It was in this room of Flamsteed House that Eddington and Dyson met with other members of a group that would form an expedition to 2 points on the Earth's surface which would fall beneath the moon's shadow during the eclipse: the island of Principe and the town of Sobral. Eddington's fervent belief that Einstein's prediction would be proved correct is attested by a story that he later told concerning that meeting. Dyson was talking to E.T. Cottingham, and telling them about the state of the experimental predictions as they saw them at that time. First, there might be no deflection. Light may not be subject to gravitation. Second, there might be 1/2 the predicted deflection, as the principle of equivalence by itself would suggest. And finally, there might be the full deflection of 1.75 seconds, and Einstein would be vindicated. Now, Cottingham, only getting the general drift of the bigger the deflection, the better, said, what would it mean if we got twice the deflection? Then, said Dyson, Eddington would go mad, and you would have to come home alone. The expeditions went out, and despite poor weather during the observations, the photographs they took of the stars near the sun proved Einstein's prediction to be right. At the joint meeting of the Royal Society and the Royal Astronomical Society on November the 6th, 1919, where the results were formally announced, the president of the Royal Society, who himself had discovered the electron, said of Einstein's theory that it was one of the greatest achievements in the history of human thought.
Those were pioneering results on light bending and made world headlines. But they were not very accurate, and the bending was partly masked by the effects of the sun's atmosphere. Nowadays, we can do better on both counts by using radio telescopes. Their advantages over optical telescopes have been exploited at Green Bank in West Virginia, looking at quasars rather than at stars. First of all, there's no need to wait for an eclipse, because the sun's rather dim in radio terms, so the quasars stand out quite clearly in broad daylight, even when they're as close as 1/2 a degree of the sun. That's about 1 solar diameter. So that's very convenient. But the real reason is that radio telescopes can be made to pinpoint a source more accurately than optical telescopes. So what is it that determines that accuracy? We have to think about the waves reaching the two edges of the telescope. If the telescope is pointing perfectly at the source, square onto it, those two waves will be in step at the two edges. That is, the troughs and the peaks will be arriving together, and they'll still be in step when they're brought to the central focus. And that means reinforcement, a strong signal. But if the telescope is slightly off the right direction, the signal is decreased because the signals are slightly out of step. How big an angle does it have to be off the source before the waves are exactly out of step so that the signal is exactly zero? The smaller that angle, the greater the accuracy. The important point for us is simply that the accuracy improves with the diameter of the reflector. The bigger the number of wavelengths across the diameter, the better the pointing accuracy. That rule applies equally to any sort of telescope, to the mirror of an optical telescope or the reflecting dish of a radio telescope. This mirror, for instance, not all that different from the mirror which Eddington used, is about 250,000 wavelengths across. So that's the sort of number we have to shoot for in a radio telescope. But 250,000 radio wavelengths, that's kilometers. There's no possible way of making a radio telescope that big. But for this particular purpose of getting good pointing accuracy, there is a way out. Suppose I wanted to widen this mirror. Because it's only the extreme edges which really matter, I can just keep on going. It doesn't matter if there's a gap in the middle. I could end up with two quite separate reflectors. That's the way to do the experiment, with separate reflectors. There are several radio telescopes here for that purpose. But to push the accuracy even further, why not increase the separation still more? There's a 45-foot telescope, 35 kilometers away. But then the signal must be brought back to be combined with that from the main telescope without losing the timing accuracy. We must know exactly how well the troughs and peaks line up. using transmission cable is not good enough. The answer was a microwave link, specially designed for exceptionally stable timing. With that, the experimenters could achieve an accuracy an order of magnitude better than that of Eddington. And by repeating the experiment at different frequencies, effects of the sun's atmosphere can be allowed for. Einstein's calculation of 1.75 seconds of arc, that's about 1/2000th of a degree, is for rays grazing the sun. But general relativity tells us also how that bending should vary with distance from the sun. And this experiment shows that as the sun sweeps past the quasars, the bending varies inversely with the distance from the sun, which is just exactly what the theory says it should do. So, using that variation to extrapolate to a grazing ray, the final result is that the bending is consistent with general relativity and it excludes anything more than 2% away from the relativistic result. That's an accuracy which is at least 20 times better than that which was achieved in Eddington's expedition about 60 years ago. This experiment measures bending of radiation by the sun, and it's a modern and accurate form of an experiment which Einstein himself suggested. But what else can radio astronomers do to test general relativity? Usually astronomers have to be content to observe. They can't perform experiments. But here's an exception. Einstein's theory says electromagnetic radiation should be not only bent, but delayed by a gravitational field. At the Haystack Laboratory, north of Boston in Massachusetts, astronomers send out radio signals and measure their time for a journey out to Mars and back to Haystack. Very high power is needed to send radio waves all the way past the sun to a planet and back again. And this radio generator, all this is one radio generator, was developed specially for this telescope, and it generates about 400 kilowatts of radio power, which is something of a record at 8,000 megahertz. And for this experiment, those radio waves are coded by reversing the phase every few microseconds in a unique way which can be recognized when the signal comes back. And of course when the signal does come back it's very weak because it's traveled so far. It may be only 10 to the minus 27 times the power which went out. That's 1 in 1,000 million times less than the power which went out. So very high sensitivity is needed. And that sensitivity comes first of all from the big size of the dish. This radio telescope is 37 meters in diameter, which is very large for a telescope which is figured as accurately as this one. And then secondly, the sensitivity is provided by the receiver. Now this is no ordinary receiver. It works on the maser principle, which means that the incoming signal stimulates emission of stronger radio waves from a ruby here, and this ruby is cooled by being in a dewar at liquid helium temperatures. And that cooling keeps the noise in the receiver to a minimum and makes for optimum sensitivity. And then finally, of course, very good timing accuracy is needed because the effect of gravity on the travel time is at most about 250 microseconds, and that's out of a total travel time which may be as long as half an hour. So to measure that with a good accuracy, a percent or better, needs a precision in the clock of about 1 in 10 to the 9th. But even so, that ranks as one of the simpler problems in this experiment because modern atomic clocks can achieve that accuracy even with a comfortable margin to spare. Well, when all this is put together, the experiment is run, the results agree beautifully with general relativity. They agree within a precision of about 1%.
The 1980s will provide a new era in the testing of general relativity. Older tests will be pushed to unprecedented levels of accuracy. and other predictions will, for the first time, be brought under experimental observation. Now, probably the longest standing of the predictions of general relativity, which as yet has not been verified, is the existence of gravitational waves. But what is a gravity wave, and how could we detect it? We can most easily understand gravity waves by trying to compare them to waves with which we are much more familiar, electromagnetic waves. Light, radar, radio waves, they're all generated when charges are accelerated in one region of space. They give off energy that moves through free space and then causes distant charges to move as the waves pass by. In the same way, if matter in one region of space is caused to accelerate in characteristic ways, it will give off energy which moves through free space and can cause distant aggregates of matter to move in characteristic ways. But if there is a basic similarity between gravity waves and electromagnetic waves, there is also a difference between them. Firstly, gravitational waves are much harder to generate or detect than electromagnetic waves are. Gravity is just a weaker force. Secondly, gravity waves have a more complex structure. We can see this by comparing the effect of an electromagnetic wave on a pattern of 4 positive charges with the effect of a gravity wave on a pattern of 4 test masses. Whereas the electric wave will cause the 4 charges to move together, first one direction, then the other, the gravity wave will cause the masses to squeeze and stretch in a characteristic movement. So general relativity makes some specific predictions about the nature of gravity waves. First, they're very weak, they're very hard to generate or detect. And secondly, they have a complex structure. They will make independent masses move in a squeezing and stretching motion. Here at Glasgow University, an experimental group led by Professor Ronald Drever is trying to detect gravity waves by looking at the motions of test masses hung in a laboratory. The audacity required to try and detect a gravity wave with such an apparatus can be made clear with one simple number. For 2 masses separated by 1 meter, the strongest gravity wave that we know would make that separation change by no more than 1/10,000th of the size of a single hydrogen nucleus. The basic idea of this apparatus is really quite simple. 2 aluminum bars, 300 kilograms each in weight, are slung from a frame, which in turn is slung from this central support. Each of the masses forms a pendulum, and the 2 are free to move in this direction. When a gravity wave goes by, it samples one component of that squeezing and stretching motion. So the 2 masses will move farther apart and closer together, but only by that most minute of distances. Now, whenever extremely small changes in distance or time of travel are to be measured, one technique comes to the fore: interferometry. In this apparatus, there's a cluster of 6 mirrors, 3 attached to one of the bars and 3 attached to the other bar. All 6 mirrors are aimed at a large circular mirror, which is attached to the aluminum plate. When the bars change their separation, 3 of the mirrors move closer to the large mirror and 3 of them move farther apart. Light from a laser is brought into a beam splitter that breaks it into 2 components. One component is then brought down to bounce on the 3 mirrors fastened on one bar. It bounces between them and the major mirror. Similarly, the other beam is brought down to bounce between the 3 mirrors of the other bar and the major mirror. The 2 beams are then recombined, then led off to a detector where their intensity is measured. An ingenious feature of this apparatus is its method for amplifying the minute changes in separation of the bars. The cluster of mirrors on each bar causes the light beam to bounce back and forth many times between themselves and the major mirror before being led off for recombination and detection. Each spot on the large mirror represents a bounce. And as it's presently set up, the light beam is bouncing back 30 times
And this amplifies the change in intensity seen in the detector. As it will be finally set up, the optics will make the light beams bounce back and forth 300 times before being led off for recombination and detection. This scope allows us to monitor the movements between the two bars. The inputs are so arranged so that when the separation changes by 1/60th the wavelength of light, the spot should execute one complete circle, clockwise if they're separating, and counterclockwise if they're coming together. Now, the system is so sensitive that it's reacting violently to the sound of my voice. But for the strongest gravitational wave that we could ever expect, we should expect that spot to move 1,000 millionth of the way around that circle. The strongest source of gravity waves that are presently imagined comes from the collapse of stars within our own galaxy. And these events are at the absolute upper limit of sensitivity of this apparatus. But in a new experiment on which Professor Drever's group is currently at work, they plan to set out 4 masses in a square 10 meters on a side. And with this apparatus, the collapse of stars within our galaxy should certainly be seen. But these events are relatively rare. You only get one every 30 years or so. So the next step is to build an even larger scale version, perhaps with masses a kilometer on a side. Then we should be able to see possibly 10 events a year, and gravity wave astronomy will really have begun.
But it may be that we are already observing indirectly the effects of gravitational radiation. The radio telescope at Arecibo, Puerto Rico, has recently observed a pair of stars that pirouette about each other in an elliptical orbit. One of the stars is a pulsar. That is, it emits radio waves in a perfectly repeating pattern. By observing the Doppler shift of this radio signal, we can study the movements of the pulsar. And this Doppler shift tells us that the pair of stars are losing energy as they orbit. So perfect is the record of their movements given by the radio pulses that we can deduce that the loss of energy must be due to gravitational radiation alone.
No physical theory can ever be proved correct once and for all. But the principal conclusion of 60 years of testing is that Einstein's general theory of relativity is correct. The magnitude of his achievement in creating the theory begins to come into perspective when we realize that on the experimental side, he had essentially only 2 scraps of information available to him in the years 1907 to 1915. The results of Oettwisch and the anomalous precession of the perihelion of Mercury. And on the theoretical side, the abstractness of the mathematical formalism to which he was driven was such that very few physicists would have had the courage to believe that it was necessary for an understanding of gravity. That Einstein's insight into the connection between the nature of space-time and the theory of motion under gravity could lead him to revolutionize our ideas of space-time while creating a theory of gravity that has surpassed every test so far devised. This is one measure of the creative vision of the greatest scientist of the 20th century.